Today, good morning, everybody. I'm very pleased to have a chance to talk about my research progress on biopolymer-based multifunctional packaging films. Let's start the very basic of the packaging. Four basic functions of packaging: containment, preservation, protection, convenience, and communication. This function is stressed in the active packaging, and the intelligent packaging stresses the communication. And with this function, for the packaging aim to improve the food quality, securing food safety, and extending the shelf life. Basically, these four packaging materials is used. Among these materials, plastics is most versatile and most widely used. Since the plastic is cheap, it's convenient to use, and has good aesthetic quality and excellent physical and chemical properties. Recently, more than 380 million tons of plastics are produced annually. Most of them is used for packaging. More than 40% of plastic produced is used packaging. But unfortunately, these plastics are not biodegradable, and more than 90% is not recycled. It caused a lot of environmental concern. I'm sure you have seen a lot of such photos. Plastics are everywhere nowadays. It causes air pollution, soil pollution, and water pollution. In addition, the discarded plastics threatens the wildlife life like this. A few days ago, I watched the TV news, which shows a man was taking out something from the nostril of a sea turtle using the plier. He put out this length of substance. It was a plastic straw. It was horrible to see. Okay, to make matters worse, the discarded plastics disintegrated in the environment to make microplastics. The microplastics less than 1 millimeter is usually called microplastics, and less than 100 nanometer is called nanoplastics. These microplastics in itself physically interfere the body, harm the bodies, and in addition, the microplastics can be used as a vector for microorganisms or toxic chemicals. These microplastics is finally come to the human body through the food chains. Now, we are aware that the microplastics are everywhere. Okay, with this background, let's talk about some more about biopolymer materials. There are two ways to handle the plastic materials, except the 3R policies. One is using plastic decomposing microorganisms. Reportedly, some plastic decomposing microorganisms are developed in the laboratories, but it's far from the reality. The next thing we can do is using the biodegradable packaging films to replace the plastic film. Mainly started with using the biopolymers. Several biopolymers are used for using developing the biodegradable films like this. I go quick. However, there are some benefits and disadvantages of using these bioplastic films. Bio-based plastics is obtained using the source, so it's annually renewable, and abundant source of materials is available. They are biodegradable and biocompatible, so it's environmentally friendly and sustainable. But the biopolymers are brittle, relatively expensive, hydrophilic, so it restricts the use of industrial utilization. To improve the property of biopolymer films, there are several methods to be used: physical method, chemical method, and cross-linking, making blend film or composite films, multi-layer films or coating films. In my first part of experiment research, mainly focused up to these levels. Later, I moved to the using nanocomposite packaging. Okay, the nanocomposite packaging adopted nanotechnology to make new packaging materials. Actually, this nanotechnology was suggested by Richard Feynman in 1959. He suggested there should be a small world we can utilize. In this small size of world, it shows some specific properties which is not shown in the physical world. This technology was later named nanotechnology by Japanese professor Norio Takuchi. Okay, actually, nanocomposite is the blending the nanoscale fillers into the biopolymer matrix to reinforce the film materials. There are various types of nanomaterials can be used depending the dimensions. It says 0 dimension, 1 dimension, 2, 3 dimension, like this. Various nanomaterials like inorganic fillers and organic fillers, organic nanomaterials have been used. Okay, in the laboratory, I used 3 different methods to make nanocomposite films. The most widely used method is solution casting method. Dissolve the nanomaterials in the solution and mixed with biopolymers and casting and drying to make film. The second method is thermal compression and melt extrusion. For the industrial scale production, we need to go to this melt extrusion method, I mean. We can expect some property increase, like mechanical properties and barrier properties and the thermal properties increase through the formation of nanocomposite. But how about the biodegradability? I marked the question mark here. Let me talk more about the biodegradability of nanocomposite films. In addition to this property increment, there is some functionality appeared through the formation of nanocomposite films. Okay. It's the tortuous pathway model to explain the reduced permeability of gas vapors. The impermeable nanoparticles is layered in the polymer layers. It prevents the passage of gas vapors, so it goes meandering like this, increase the path length. That's the way it shows the reduced water vapor permeability or gas vapor permeability. It's called tortuous pathway models. Okay, first, researchers on the biopolymer nanocomposite film, like Tito and Shina Reis, prepared nanocomposite films using PCl and PLA-based composite film. They added nanoclay and tested biodegradability. They found the biodegradability of nanocomposite film is increased, easily degrade than the neat polymers. They explained this increased biodegradability is due to the catalytic action of nanoclay. Okay. Sometimes the previous researchers published something. People usually think it is the truth. Therefore, the subsequent researchers come up with a different result. It's very difficult to explain. It's not easy to accept the result. This proof is more harder than proof. The case is with Professor Lee at the Busan University. Professor Lee prepared PBS-based nanocomposite films using the nanoclay called closite 30B. He found this result. The degradability of a composite film is lower than neat films. It against the previous result. First, they submitted this result to the biomacromolecule journals. The reason is not consistent with the previous result. So they submitted to this journal, polymer journals. They published this result and explained the reason to reduce the biodegradability is due to the microorganisms diffuse hard due to the clay materials using the tortuous pathway models. Everybody here is this explanation is not correct because Lee is a polymer engineer. He's a lack of expertise in the microbiology. later, we made chitosan-based composite films using both sodium mormonite and chlorite 30B. Chlorite 30B is the same as Professor Lee used, and chlorite B is organically modified mormonite. Through this experiment microbial test, we found chlorite 30B added 1 has a clear antibacterial activity. So we confirmed this result using the total colony count method and found this chlorite 30B added 1 has a clear, strong antibacterial activity. We finally conclude this antibacterial activity of chlorite 30B is due to the quaternary ammonium salt used to modify this clay, mormonite. Okay, this one has antibacterial activity. That's why it reduced the biodegradability of composite films. After this work, I switched to my research work to multifunctional nanocomposite films. I tested almost all types of nanocomposite materials to develop biopolymer films focused on the active and intelligent packaging work. One example of making nanocomposite films, we prepared 6 different types of zinc oxide to make composite films and found it has strong antimicrobial activity like this. This one is also make PLA and zinc oxide composite films, so the strong antimicrobial activity. We made another type of zinc oxide functionalized halloyside material. The zinc oxide was attached, adsorbed to a halloysite nanotube. This one also strong antioxidant activity. One interesting with this is actually the halloysite is hydrophobic. It's not dispersed in water. After modification, it shows increased zeta potential. It means it more easily dispersed in the solution. After that, we tested various types of nanomaterials like this and tested all the functional properties. Most of these functional nanocomposite materials shows antimicrobial, antioxidant, and UV barrier properties. So you can choose any materials depending on the final application. Next, we go over to the quantum dot materials for making composite materials. The quantum dot material is developed as a semiconductor. Excuse me. Semiconductor nanomaterials with the sizes less than 10 nanometers. It shows clear fluorescence. But this semiconductor-based quantum dot usually based on the metallic-based ones, so is toxic. Cytotoxicity is high, so it cannot be used in the food packaging applications. So we focused on the non-metallic quantum dot like carbon quantum dot and the sulfur quantum dot material. Okay, carbon quantum dot is a kind of new class of nanomaterials based on the carbon-based material. The size is less than 10 nanometers. Actually, this carbon quantum dot was accidentally found by the Su et al. In 2004. While they are purifying the carbon nanotube, they accidentally found these materials. After that, these materials has been used various fields of industries. I interested in the many focused in the packaging applications. There are various attractive properties of carbon quantum dot. One application part is reinforcing the nanocomposite using nanomaterials like carbon dot, and it has a strong antioxidant, antimicrobial, and UV barrier properties. So we can use CD to develop multifunctional nanocomposite films. It can also be used as a nanosensor for monitoring the shelf life of or color change of food and the detection of some hazardous food chemicals. Carbon dot materials are usually used two ways, top-down method and bottom-up method. In the laboratory, one of the bottom-up method of hydrothermal method is most widely used to produce carbon quantum dot. Recently, the carbon quantum dot is produced using various biomass, using food processing waste, or microorganisms, or some plant material. The carbon quantum dot materials can be used as a coating of food, or carbon quantum dot can be made for composite films for active packaging applications, and carbon quantum dot itself can be used as a food additive because it has a strong antioxidant and antimicrobial activity. We made carbon quantum dot using glucose and characterized the carbon quantum dot developed from glucose, and it shows a strong antioxidant activity against the ABTS method and the DPPS method. The antioxidant activity of carbon quantum dot is comparable to ascorbic acid or higher than ascorbic acid. One interesting thing is of carbon quantum dot is it shows the color change depending on the pH. So it can be used for detecting the color variation of food material. It also shows strong antibacterial activity like this. We made carbon quantum dot using nanofields. It shows the antibacterial activity and antioxidant activity. This film Quantum dot added film was used for packaging of meat. It shows the quantum dot added to the chitosan film to make computer films. This film was used to packaging this meat. Okay, it's the control. The microorganism is included during the storage. This one is the chitosan films. It shows some delaying the growth of microorganism is due to the antimicrobial activity of chitosan itself. When we added carbon quantum dot, it reduced drastically the microbial count like this. Recently, we made carbon quantum dot using 3 different types of coffee beans. Low coffee bean and the low seed coffee bean and the spent coffee beans using the hydrothermal method and characterized all the properties. We found morphological or chemical, some other functional properties of these 3 carbon dot that's very similar. In that case, which one do you choose for the source of carbon quantum dot? The answer is very clear. Okay, I'll go quick. I'll skip this. Next one is use of sulfur materials for developing the functional films. Sulfur. In olden times, sulfur was produced in the volcanic areas, but recently, plenty of sulfur is obtained as a byproduct in the petroleum refining industry. This sulfurization produced more than 70 million tons of sulfur every year. Surplus 7 million tons every year. It stockpiled like this. It causes another environmental problems. So we try to use this sulfur for functional packaging applications. Okay. We made 2 different types of sulfur nanoparticles, sulfur nanoparticle and sulfur quantum dot. Sulfur nanoparticle and sulfur quantum dot, such application areas. It's the summary of a way of making sulfur quantum dot. I'll skip. It's the one way to make a sulfur quantum dot using hydrothermal method. We compare the property of elemental sulfur and the sulfur nanoparticles and the sulfur quantum dot. The side is the morphology of its materials. These 2 sulfur nanoparticles, elemental sulfur, sulfur quantum dot. There is a huge difference in the size. It's the micrometer size is almost 100 nanometers. It's less than 9 nanometers sulfur quantum dot. The property is also different. The sulfur quantum dot has fluorescence properties and also higher antioxidant activity and antimicrobial activity compared with other 2 materials. Okay. Sulfur quantum dot added alginate film shows the same antimicrobial and antioxidant activity. We apply this film to packaging the bread the other elemental sulfur and the sulfur nanoparticle added one shows the clear growth of mold after 14 days, 2 weeks. But this one still shows very clear without mold growth. We use the sulfur quantum dot to coat the inoki mushrooms and found the extension of shelf life of inoki mushroom. Okay, shows the functionality of quantum dot, high antioxidant activity, antimicrobial activity. It shows the mechanism of antimicrobial activity of the sulfur quantum dot, the same one. Recently, we found the sulfur quantum dot has anti-inflammation activities. It can be used for a biomedical application too. It's a cytotoxic test. Sulfur quantum dot shows the same growth of mouse fiber blood cells as a control, but the sulfur nanoparticle has some toxicity. But the sulfur quantum dot does not show such toxicity. It's the same safety test. I'll skip this. We use the sulfur quantum dot for, we added the sulfur quantum dot solution to the fountain pen and wrote these fine figures. It's not visible in the visible light, but under the UV light, it shows clear letters or figures. How can you use? It can be used for anti-counterfeiting packaging. Recently, we also tested the sulfur quantum dot to recognize the fingerprint. It shows very clear fingerprint using sulfur quantum dot. Unfortunately, I'm not show here. It's another new step of interesting research using the sulfur for making the sulfur polymers. But I'm afraid I have short time to explain this. Just to show the picture. I should explain this. The sulfur. Sulfur is powder forms. The sulfur is usually has 8-membered rings like this. But if heated the sulfur more than 159 degrees Celsius, it dissolved. It melts like this. And above this temperature, there is a ring opening of sulfur to make reactive diradicals. This diradical is very reactive. It can polymerize to make a long chain of sulfur. But if the temperature is reduced to room temperature, go back to this state. It's the backbiting mechanism. So if we prevent this step using double bond systems, we can make some sulfur-based biopolymers. This technique is called inverse vulcanization. It's coined by Jeffrey Pyun in 2013. There are a lot of application areas of this technology, I think. skip here. It's a recent result of using sulfur. Using the inverse polarization method, we made sulfur chitin complex using this inverse polarization method. And this sulfur chitin complex was added to chitin films to make a compact film. This film shows strong antimicrobial activity and antioxidant activity and high UV barrier properties. It's the beginning of use of biopolymer-based high sulfur containing polymer film work. Okay. I'd like to conclude here. Food packaging is an art, science, and technology for safe delivery of food to the consumer. It is interdisciplinary science. Most of my research work borrowed from other areas. The main technology I adapted from other areas, nanotechnology, the quantum dot, and apply in the packaging applications. So we need to collaborate with other areas. So finally, I'd like to conclude my talk. Food packaging is always innovative, dynamic, and futuristic. Thank you for your attention.